is a method which is used to calculate slope and deflection of beams at different points. So what is this moment area method? So moment area method basically consists of two theorems. So in the first theorem deals with calculation of slope, and the second theorem deals with the calculation of vertical deflections. So the first theorem says that if we consider a beam which is loaded by any kind of load, then we know that due to this load it will undergo some bending, and this bending is represented by this elastic curve, right? So the deflected shape is represented by this elastic curve. So the theorem 1 says that the angle between the tangents at any 2 points on the elastic curve equals the area under the M by EI diagram between these 2 points. So let us look at this statement in parts. So first says the angle between tangents at any 2 points. So let us consider point A and B on the beam. So in the elastic curve, these points are shown here, A and B, after the deflection. So if I mark a tangent at point A, so this is tangent at A, and if I mark a tangent at B like this, so the angle between these tangents at any two of these points, so as you can see here, I have marked here angle theta BA, which means it is the angle of B with angle of tangent at B with tangent A. So the theorem says that this angle theta BA equals the area under the M by EI diagram, these two points, right? Now this is the second part of the theorem which I have underlined. So now our motive is to calculate this theta BA. So this theta BA is calculated or determined on the basis of the M by EI diagram. So what is this M by EI diagram? You all know how to, we have already studied how to draw the bending moment diagram for any beam. So M diagram is the moment diagram, bending moment diagram. If we divide all the bending moments value by EI, which is the flexural rigidity of beam, then we will get M by EI diagram. So if this is the total M by EI diagram of this beam, then this theta can be determined by this formula. So this formula basically means that the theta BA is equal to area of M by EI diagram between A and B. So if out of this whole diagram, bending moment diagram, I calculate the area of only this shaded region, so that area will give me the value of this angle theta BA. So again I will repeat. So in this theorem, the angle between tangents of 2 points on the elastic curve is equal to the area of the M by EI diagram between those 2 points specifically. So here we will not take the bending moment area of all of this whole of this bending moment area. We will take only the M by E area between these 2 points A and B. Regarding slope, now we move to the next theorem, which is theorem 2, which is used to determine the vertical deflection of any point, right? So what is the second theorem? So the second theorem deals with the vertical distance, as I have told you, that is the vertical deflection. So here let me read the statement first. If A and B are 2 points on the deflected shape of a beam, so like I did previously, I have drawn this green curve, which is the elastic curve that is representing the deflection of the beam. Now I take any 2 points A and B between them, right? So these are these 2 points. Now in the previous theorem we had calculated the slope, or the is theta. Now here we will calculate the vertical distance. So the vertical distance of point B, so keep watching this elastic curve side along with the statement. So vertical distance of point B. So here is the point B, and this is the vertical distance from where? From the tangent drawn to the elastic curve at point A. So if I draw a tangent at A to this elastic curve, and if I calculate the distance of B from this tangent, then that will be represented by TBA. So this is the TBA's vertical distance. So note here, I have written here TBA, and another I have not written it TAB. So what is the difference between these two? You must be very clear about it. TBA means that we are calculating the distance of point B from tangent at A, right? So I am calculating basically the distance of point B here. So I have written TB first, B first. If I want to calculate, if so I will show in this diagram, if I extend this tangent at B like this, and if I calculate distance of A from this tangent at B, then this will be TAB. Understood? So this is the difference between TBA and TAB. So according to the requirement of our question or problem, we will use either of these values, right? So here, so I hope you are clear what is TBA. So for now, I am removing this TAB. I will be just dealing with this TBA. So TBA is distance of B from tangent at A. Now we have seen what is this TBA. Now how to calculate this TBA? So this distance is of M by E of M by E of M by E of M by E diagram between these 2 points A and B about the point B, right? So this is mistakenly written here, about the point B. So what does moment of area means? Moment of area basically means it is the multiplication of one value with the distance, right? So what is that value? Moment of area. Moment of area of M by EI diagram means that we are multiplying area of M by EI diagram with some distance x bar, right? So this is termed as this, the term coined for this value is moment of area, right? So moment of area of M by E diagram is basically area of the M by E diagram multiplied by x bar, and this x bar is what? So here I have written here, so x bar is the distance of centroid here, at the bottom also. So xb bar is the distance of centroid of area measured from B in case of TBA, right? So for calculating TBA, what we will do is first we will find out the area of bending moment diagram, which is this. Then we will multiply it with the value x bar. So here you can see in this figure, we are considering 2 points A and B, so we will be taking only this much area of bending moment diagram, M by EI diagram. So the M by EI will be the area of this shaded region into x bar B will be the distance of CG of this area from point B. Tangent at A. So TBA will be M by EI diagram, area of M by EI diagram into XB bar, right? Where XB is the, so I can write it like this, TBA is area of M by EI diagram between A and B into centroid of area measured from B. Similarly, if we are determining TAB, which is the vertical distance or deviation of A with respect to tangent B, then it will be represented by TAB, and here it will be Tx bar star, where Tx bar star is the centroid measured from A of the area. So if I show in the previous figure, this will be x bar star, that is distance of this G, which is the centroid from A. Okay, so this is the theorem 2. So I hope you are clear that how we can find the slope as well as deflections from moment area method. Now we can summarize now that in order to calculate theta or slope or deflection y, we need uh, three parameters which we must know. First, we must know the bending moment diagram of that particular beam. Of course, we cannot solve this moment area method without the bending moment diagram, because from this bending moment diagram we will draw the M by EI diagram, right? Next, we must know the area of the M by EI diagram. So when we have drawn the M by EI diagram from the BMD, so depending on its shapes, we will have different areas, right? So as you have studied earlier, there can be different shapes of BMDs. Therefore, their areas can be different. So we must know how to calculate those areas, and we must also know how to locate the centroid or CG of those areas, because when we are calculating the deflections we have to multiply the area with the x bar, so we must know the location of centroid. So for this I have put here some common shapes of BMDs, and I have um, here this picture is representing the areas of these areas of these shapes and their location of their centroids, right? So here this is a rectangle, these are triangles, this is a parabolic curve, this is semi-parabolic curve. So we will be using these depending on the type of beam and type of loading which we have, right? So let us take some examples on this. So first, let us try to solve this question. So here we have a cantilever beam which has a point load acting at its free end. It is of length L, and we have to find the slope and the deflection at point B, right? So always remember, whenever you are solving any such question, the first step should be you must be have an idea about the elastic curve or the deflected shape of the this particular beam, right? So because we need tangents at different points, so first I will draw the elastic curve. As you know, this is a cantilever beam, so it will deflect like this. So this black line here is representing the deflected shape or the elastic curve of this beam, right? Now what I do is I take any 2 points A and B, right? So I have taken this first point A and this second point B, which is the free end, right? Now why I have taken these 2 points, there is also a reason for this. We want to find out theta B, right? So there is no direct way to find out theta B, but from moment area theorem 1, we know that theta B, BA is the area of M by EI diagram between A and B, or any two, there can be any two arbitrary points, right? So which should be, so first point is where we want to calculate the theta, that is B, and the second point here is the second tangent, right? So which second tangent we should take, right? So I will give you an example. This is an elastic curve and there are many points in this curve. We are concerned with this point, which is point number B, because we want to find the slope here. So first tangent, of course, we will draw at B. This is very clear to me, right? I will draw the tangent from B, like this is the tangent at B, right? Now out of these all points, this point will also have a tangent like this. We can draw the tangent like this. So there are many types of tangents, many types of points on this curve, and we can draw their tangents also. So which tangent should we take? That is very important. Which point should we take? So for calculating theta B, so I can write this equation like this. that theta b minus theta a is equal to area of m by ei diagram between a and b. So now we want to find out theta b. So for calculating theta b, we must know what is theta a, right? So always choose the second point as that point whose theta we are sure, whose value we are sure about. So in this curve, as you can see, there are different points and there can be different values of theta. But why I have chosen here this A point, because as you know from basics that this is, if there is a fixed beam, then there is no rotation and there is no vertical displacement, there is no horizontal displacement. So I can say that theta will be 0 for this at this point. So we know the value that theta A is equal to 0 in this case. So if I put here 0, so my direct I will get theta B is equal to area of m by ei between A and B, right? So we have to change this equation according to our requirements so that we can solve, right? So it is very clear in case of cantilever beam we have no problem, because fixed in for the fixed support the slope will be always 0, so we can take the fixed end as the relative tangent, right? So here as you can see, in this case I have drawn two tangent. One is the tangent at B and another is tangent at A, and because there will be no rotation at A, so its tangent will be horizontal, right? Now the angle between these two is theta BA, which we have already talked about. So I want to calculate this theta BA. So how should we calculate this? We know that theta BA is area of EI 1 by EI diagram between A and B, right? So we know this formula. So first we have to draw M by EI diagram, and for drawing the M by EI diagram, we must draw first the bending moment diagram, right? So we all know how to calculate the or plot the bending moment diagram. So moment at B will be 0 because this is a free end, and moment at A will be, so moment at A due to this load will be P into L, and this will be minus, right, due to the sign conventions. So we can draw the bending moment diagram like this, that so this will be negative minus PL, right, and here it is 0, here it is minus PL, and we will join this with the help of inclined line. So this is the bending moment diagram. Now how to draw M by EI diagram? Just divide these values with EI. So M by EI diagram will be the same, just in place of minus PL we will have minus PL upon EI, right? So now we will be using this M by EI diagram. Okay, so first we will calculate the slope at B. So slope at B, theta B can be calculated by theorem 1, right? So we know that theta B is equal to, this is the mathematical expression, M by EI A to B, right? So theta BA will be angle which tangent B makes with tangent A. It will be area to M by A diagram between A and B. So I can write theta BA as theta B minus theta A, right? And we know theta A is 0. Okay. Also, the area of M by EI diagram is, so if I mark these points, this is B, this is A, and this is A dash. So area of this M by EI diagram will be area of this A, B, A dash, right? So theta B minus 0 will be area of this whole shaded region. So now I am taking the whole shaded region because we have to find theta BA. So we have to take the bending moment diagram between A and B. So this is basically the complete bending moment diagram, right? So we will take this whole area. So it will be half, this is a triangle, so half into base into height. So base is here, this is length L, and this height is PL by EI, mine with negative sign. So it will be half L into minus PL by EI. So we will get theta B equal to minus PL square upon 2EI, right? So quite easy to understand. right? This is how we calculate slope. Similarly, we will calculate the deflection. So I will use the same diagrams here also. So for calculating deflection, we will use theorem 2. So in the elastic curve, TBA, so now you can see that we want to calculate YB, right? So YB means this value we want to calculate, okay? Another thing is, this is my elastic curve and this is point B and this is the tangent at A. Now what is this distance called? This distance is also called TBA because this is the vertical deviation of B from tangent A, right? So this is represented as TBA. So I can say that YB can be is equal to TBA. Understood? Because YB is the deflection at B, which is also this value, and TBA is also the distance of B or deviation of B from tangent at A, right? So YB is equal to TBA. Okay. Now from theorem 2, we know that this TBA can be determined now by using this equation. Okay. So see how we proceed. We want to find out YB. So first we want to relate it to our theorem, right? Our theorem does not, moment area method does not always say that theta B will be this or YB will be this. It says in terms of theta BA and TBA. So we have to utilize it according to our question. So in the question which we are currently doing, it is easier for us to relate TBA with YB and theta BA with theta BA, but always this is not the case. There can be some complicated cases also which we will learn. So TBA will be this, the area of bending moment diagram into the centroid, and that will be measured from point B. Okay, so TBA is area of M by EI diagram between A and B into centroid of area from B. So if this is, for example, the centroid of this triangle, right, and we will take the area of M by EI diagram between A and B because we have chosen both the points A and B, right, because tangent at A will be horizontal, so it will be easier to calculate. So X bar will be the location of the centroid from point B. So this will be X bar. Why B? Because we are calculating TBA, right? So we will take distance from B. So area is already, we have calculated area, that was minus PL square by 2EI into X bar B. So this is in a triangle, you must know that this value is 2 by 3rd L and this value is L by 3, right? So we will take 2 by 3, so we will get minus PL cube by 3EI. So this is how we calculate the deflection and the slope at any point, right? Now let us take another problem. So in the next problem, again we have a cantilever beam, but here the load is placed at the center, right? Because this is L by 2 and L by 2. Now like we did earlier, first we will draw the elastic curve. So always in any any kind of uh, cantilever beam, if this is the actual shape, the deflection will be like this, right? So here the load is acting up to this point, so the deflection will be like this, and after that there is no load, so it will be somewhat straight, right? So we will get a similar, but here it will be not curved, and here it will be here it will be straight and here it will be curved, right? If there is a load here. Okay, so such kind of elastic curve we will have. Okay, so again we will consider A as tangent A, so we will mark tangent A horizontal and tangent B like this. So theta BA will be this. So again here also we want to calculate yb and theta b. So theta b can be calculated from theta ba directly by using theta ba is equal to theta b minus theta a, and tba is equal to yb, right, as already explained in the previous question. Right, now we will draw the bending moment diagram. So here for this bending moment diagram there is no load here, so there will be no bending moment here at this C point, and at A point the maximum bending moment will be PL by 2, right, so this will be negative. Okay, and here the bending moment will be 0, and the MIEI diagram will be like this. Okay, so this is the MIEI diagram. Okay, so in AC portion we have a shape, and in CD portion we don't have any type of shape. So to calculate slope, we will use again this theorem 1, theta b is equal to the area of M by A diagram between A and B. So see here carefully, although we have to consider A to B, the area of complete this M by A diagram, but the bending moment diagram is just this much. So we will have to consider this much area only. So the area of this area will be half into this distance, which is L by 2, into this distance AC dash, which is PL by 2EI, right? So it will be area of CAC dash. So we will calculate. So theta BA minus theta A will be this, and theta A will be 0. So we can write like this, right? So theta B will be minus PL square by 8EI. Okay. Similarly, we can solve the deflection also. So for the calculation of deflection, I will solve it here. What we will do, TBA is equal to YB, right? TBA will be equal to YB as we know. So which can be calculated by area of M by EI diagram between A and B into centroid of distance of centroid from point B, because we are finding TBA. So see in this triangle, the CG is located at this point. So we know from the CG of triangle that this should be 2 by 3rd of the base of the triangle, right? So if this is a triangle, this is the base. So this distance is 2 by 3rd of B. So it will be 2 by 3rd of L by 2. But we want to calculate the distance of this centroid from B. So that will be L by 2 plus 2 by 3rd into L by 2. Okay, so I will write it this way, that area is minus PL square by 8EI, we just calculated, into 2 by 3 L by 2 plus L by 2. Okay, we can solve it to calculate YB. So after solving it, we are getting the value of YB as minus 5PL upon 48EI, right? So this is how to calculate slope and deflection. Now another question for the same. So we have now a cantilever beam having a UDL, right? So we know for a UDL what do we do? For a UDL, we have first again we will have to draw the elastic curve, so it will be similar, right? We mark the angle theta BA and the distance TBA, then we calculate the bending moment diagram. So you know that bending moment at B will be 0 and bending moment at A will be WL into L by 2 negative sign. So it will be minus WL square by 2. So this will be minus WL square by 2, and because this is UDL, we will have to join B and A with a parabolic curve, right? So this is the parabolic curve, and the M by A diagram will be same, just we will write minus WL square by 2EI, right? Now we want to calculate theta BA, theta B. So theta BA will be theta B minus theta A, which is equal to area of the bending moment diagram between A and B, because we have taken the 2 points at A and B. So this covers the whole of the portion of beam. So area of BAA dash. So now this is a semi-parabolic area, right? So the area of this type of shape is 1 by third. So if this is B, this is H, this is 1 by third B into H. Okay, so now this is area is 1 by third B into H, and we know that theta A is equal to 0. So we can write that theta B minus 0 is equal to 1/3 of, so 1/3 of this distance into this distance. So this distance is L, this base of this semi-parabola, and height is minus WL square by 2EI. So it will become minus WL cube by 6EI. Okay. Now for calculating the deflection. So for deflection, it is very simple. We just have to multiply this area of MIA diagram with this location of CG. So for first we will locate the CG. So CG is measured from B, because we have to find out TBA, because we are finding distance of B with respect to tangent at A, right? So we will take the distance from B. So for a semi-parabolic curve, the centroid is located at distance of 3 by 4 from this point, right? So it will be area into 3 by 4L. So we will get minus raised to power 4 upon 80I. So very simple. Once you know how to draw the M by A diagram and how to draw the elastic curve, there is nothing much difficult. Now the next question is again for a cantilever beam, but it is subjected to a bending moment and not at B. There is no force. So again, the irrespective of any force, the deflection will be like this. So again we make the elastic curve and the tangents. We show theta BA and TBA and YB. So TBA will be equal to YB. Now for the bending moment diagram, as here bending moment is acting at point B, so we cannot say that bending moment is 0. So it will be minus m naught at bending moment at B will be minus m naught, right? And bending moment at A will also be minus m naught. Okay, so we will get such kind of this BMD, and this will be both minus m naught and minus m naught values. Okay, so M by A diagram will be same, just minus m naught by EI minus m naught by EI, right? So this is a rectangular shape now. Okay, so slope at B will be theta B A is equal to theta BA minus area of this complete M by A diagram, because we are taking these 2 points A and B. So we have to calculate the area of this rectangle A, B, B dash, A dash. So what is the area of rectangle? It is the multiplication of the two sides. So this is minus m naught by EI, this is L. So we will get this theta B. And for calculating deflection, we will again use TBA, which is equal to YB. So for this, we multiply this area with the centroid measured from B. So centroid of this rectangle will be L by 2. So we will get area into centroid, which is measured from B. So it will be minus m naught LEI into L by 2, because distance from the CG from B is L by 2. YB as minus m naught L square by 2EI. Okay, so this is how we solve different questions for slope using the moment area theorem.